Hello. Hi guys. Today we'll be discussing a very important topic that is machine learning algorithm, which is SVM. SVM is doing what? Support vector machine. You can see here, we first of all we'll be doing something called understanding support vector machine algorithm from examples. So we'll be understanding how the support vector machine works. Then after we'll be doing something called the math behind this support vector machine. Okay, this support vector machine is implemented in Python as well as in R. It has some different applications. It has some pros and cons, and mainly the thing is it can be used for classification problem as well as regression problem. First, we will be doing classification problems, and what are the things which comes under classification problem. We will know. See, the first question: what is support vector machine? Support vector machine is a supervised machine learning algorithm which is used for both classification and regression challenges. As I said, it is mostly used for this classification problems only. And here you can see the diagram of y and x. So x is a independent variable and y is a dependent variable, and we are predicting some values of y with the help of x. These are the data points which are well distributed. So we are separating this. Let's suppose take this points. This red points as negative and this green points as positive. So we are separating these points with the help of some hyperplane. Same as logistic regression, we'll be having the certain parameters like slope as well as y-intercept for this particular hyperplane in order to separate or in order to divide this uh, in order to classify this two different types of classification. So the first step is to divide this particular support vector data points with the help of hyperplane. Then what we'll be doing? So so after that we have a use case scenario, that is to identify the right plane. First scenario is to divide this particular data points into positive or negative or class A and class B. So in this diagram there are three particular hyperplanes are there. So we have to describe, and we have to find which particular hyperplane will divide or will classify this particular problem into class A and class B. Here you can see the C B. B is a correct hyperplane, which can be said that it is a best hyperplane by looking at this particular diagram, which is separating these red points with green stars. So after that, we have to identify the two planes which are uh, let's suppose if you take the C as a mid hyperplane, or the SVM, the main SVM is to draw two more hyperplanes which are parallel to this particular plane C in such a way that the the data points will be nearest to that particular plane. Let's say if you take B here, this star is very near. This particular data point is nearer to this B, and if you take this particular A, this red dot is very near to B. Yeah, yeah. I mean this line is passing very nearer to this particular data point. This is known as SVM, where we'll be having one mid hyperplane, and apart from that, we will be segregating that hyperplane into two parallel hyperplanes in order in such a way that the data point will be passing through. The nearest data point will be passing through that particular hyperplane. Okay, you can see here. And one more thing, there are some parameters I have to explain. One is support vectors. There are some parameters we want to know in this support vector machine. One is support vectors and hyperplanes and marginal distance and linear separable and non-linear separable values. Okay. Here you can see there are some scenarios where in real data there are some scenarios where um, this particular star will be here, and this particular star is outlier where here it is somewhere it is differently placed. So you can see here there are some scenarios where this red dots, this one type of data is in circular mode, and which is circling another type of class B. There are data some type this data, how we can segregate that, how we can do, how we can solve this problem using SVM. We will be discussing that. Okay, let's math intuition behind SVM. I'll be explaining that. In that, I'll be explaining this all the terms: support vectors, hyperplanes, and marginal distance, and linear separable, non-linear separable. Okay, as we know, the straight line equation is given. Here you can see the diagram. The straight line equation is given by y is equal to mx plus or w transpose x plus b is equal to 0. Here it is written minus b, but the actual thing is plus b is equal to 0. Okay, w2 plus x minus b is equal to 0. Okay, then what we have to do, so here I am considering this green points as positive values, and the blue points as positive values, and the green points as negative. Okay, and I'm considering some kind of slope for this particular diagram, and some slope as well as some y-intercept value, that is b value, for this particular diagram. You can see here, after deriving this particular hyperplane, I am also deriving two hyperplanes, this one and this one, which are parallel to each other, in such a way that this particular plane will pass us through some data point. This also will pass us through some data point. Here our main aim is to maximize this particular margin. Margin is nothing but the difference or a distance between this particular mm, parallel planes. This plane and this plane. The main aim is to maximize the distance or a margin value between these two planes, so that we can achieve a very good accuracy and very good model. Okay, fine. See here, here it is explained perfectly. Wx w to the transpose x, wt x minus b is equal to minus 1. It says that anything or above the boundary of a class 1 is labeled as 1. This particular blue lines are 1 value with 1. This particular green lines are value with minus 1. Okay. Here we have two case scenarios in such a way that if w transpose x minus b, which is greater than 1, if y of I is equal to 1. In the sense, the straight line value will be always greater than 1 if y of I is 1. If y of I is 1, then this particular value is always 1. What else? In the same way, the values, let's say this value, this is plus 4 plus 5. Let's take some value of plus 4 plus 5. So if you put those values here with slope, we will be getting the value of y will be in minus. If we if consider this coordinates of this particular blue line, when we will be putting that particular values, this particular equation, that straight line equation, we will be getting the value of 1. Says that the anything above this line will be considered as plus value, anything below this line will come as a minus value. Okay. And one more thing I used to say, see here, I'll be explaining the important terms here, which is very useful while in cracking an interview with respect to this SVM. First, this particular line is known as hyperplane. These are two hyperplanes which are derived from this particular hyperplane, which are parallel to each other. Then the particular data points which are passing through this particular line, and this particular line, we call this particular points as support vectors. The support vectors are which helps support vectors helps to maximize the margin value in order to get in order to classify the particular model at a very good um, in order to in order to classify the model at a very perfect level. For a good classification. Okay. Now after that, that is there is hyperplane. This particular red line is known as hyperplane. Okay. Then the marginal distance, the difference between these two, this and this particular known as margin. So margin, you can say margin. This is margin. The margin is defined by 2 by a normalization of W. Then after that, linear separable. Linear separable is nothing but we are separating this particular. Let's take this example. We are directly separating this particular data points with the help of straight line. This is what a straight line. By using this straight line, we are separating just a line. We are separating this particular data points. What in case if the data points are in circular mode? Let's say I'll show you. Here you can see the data points the red data points are in circular mode. Around that, this particular another class B class another class of data points are distributed. In this case, what we have to do, we have to use something called SVM kernels. SVM kernels will help us to convert this particular 2D, this particular diagram is 2D now. To convert this particular low level dimensional models to low level dimensional models to or a graph to high level dimensional graph. Let's say this is a 2D graph. So if then what we are doing, we are converting this particular 2D graph into 1D graph. Sorry, 2D graph into 3D graph, so that by using this 3D graph we can separate this particular we can easily separate this or we can classify this with the help of easily classify this with the help of linear model or a linear separable model or linear separable line or hyperplane. So the way of doing the way of converting the 2D models into 3D models, that is the main function of this particular SVM kernels. Okay, so you can see as explained, this is very simple. I mean, for implementation, we the thing is the main thing is for any interviews or for anything, the main thing is we have to understand what is support vector machine and what are the math intuition behind it. And for implementation, it is very easy, as simple as we are implementing this logistic regression. Here from this, we have to import something called SVM. From the second line, we have to import SVM model, and pandas is common, and accuracy we are for metrics for measuring loss function. We are for measuring the score, we are importing this accuracy. So you can see first we are reading this particular dataset, that is train dataset, train X, train Y, training dataset. In that train wise target variable, that is loan status. We have to classify whether a loan, we have to what is the status of a loan of a particular person, and train next is some amount of features which are deciding that we have to what is the loan status of that particular person. And we have some test data, this particular loan dataset. So you can see here, I am building SVM model. This is implementation support. I'm giving some name support is equal to svm dot linear svc. Linear svc is nothing but the data points are linear in nature. So first we are trying with linear model, okay, and random state. These are the some parameters which will be giving, okay. Then we have to fit this model, with the training data set and level data set. Then after that we can predict the model. After that we will be getting the results. Then we are then we are converting this particular data set into CSV for further validation. See, wait a second. And there are so many hyperparameters. Likewise, you can see uh, the kernels, SVM kernels, which SVM kernel we have to select. There are so many kernels, and the degree, how much other degree will be differing. The gamma value, string value, probability value, and cache size, class weight, scope was maximum, iter, random state, etc. I have to explain this particular C. What is this C value? C is nothing but errors. C is nothing but a penalty parameter C of an error attack. Let's say in this particular diagram you can see that, or else I can explain you in some other diagram. Here you can in this particular diagram you can see that this all are one class. These all are one class. If we do SVM, if we implement SVM model, here we can get this particular best hyperplane. After that, we'll be drawing another two parallel hyperplanes. But the thing is, this particular this particular, we can say this particular data point is misclassified. It will be misclassified. It is a some outlier. It will be misclassified. What we have to do in that particular such cases? Like in logistic regression, it will be classified as a red point. So in logistic, the main new thing in SVM is C value. We have to give C value. C value is nothing but a number of errors in that particular model. If this is a C value, this particular point is considered as the value C value. I mean, here this is a one error, or else I can say here. Let me explain. Suppose this is suppose consider this particular diagram and this particular data set. The training has been done and we have to do testing. Let's suppose we'll find some of the red points at this between this B and C, between this B and C, and some data green stars are between this C and A. But as per this particular SVM implementation, it will be considering as it will be considered as a misclassified model, or it will throw an misclassified model with a less accuracy. Okay, what we have to do, we have to give something called C value, that is a number of errors in that particular model. Okay, let me explain this. So here they have taken iris data set, that is iris flavor data set. We have to define some value. Here you can see linear separable model. Red dots uh, separable models. This particular diagram has been separated into three different. You can see using RBF kernel. This particular linear model has been a linear model has been converted to this particular some kind of non-linear structure. After that, you can see the gamma value. Now, what exactly the changes in gamma value and what exactly changes if we change the C value. C value is nothing but errors. Let's suppose there are so many points, so many data points will merge together. So we have in that merged region, we have in that merge the data points which get merged, no, that data points will be considered as this error. We have to give that particular. You can see for C is equal to 1, this is a model. And this is the data points distribution. For C100, this is a data point distribution. For C1000, this is a data point distribution. For you can see here how the particular data points are being classified. So kernel parameters can be tuned like linear, poly, RBF, poly, or re. Coming to the last topic, that is pros and cons associated with this. It works really well with a clear margin separation. It works really well with a clear margin separation. If the margin is clearly separated, then the model accuracy is very high when compared to logistic regression. It is effective in high dimensional spaces. Effective in the sense, if there is so many dimensions, like so many dimensions is nothing but if we have so many features for a particular model, then the accuracy is very. It is effective in cases where number of dimensions are greater than number of samples. Here it is saying that if the number of features are greater than number of samples, it uses a subset of training points for a decision function called support vector, so that it is called memory efficient. And like I said, for training, it uses subset of training points for decision function for making a decision. It will be using something called support vectors. Depending upon support vectors only, we are deriving these hyperplanes, parallel hyperplanes. Cons. When coming to disadvantages, it doesn't perform well when we have a large data set because the required training time is higher. As said, it requires some time and it cannot be a very good algorithm for large data set. It doesn't perform very well when data set has a more noise and the target classes are overlapping. Like I said, in real world case, the more data points will be overlapping. So in that case, this is not a very good model, or this is not a very good algorithm. SVM doesn't directly provide the probability estimates. These are calculated using expensive 5-4 cross validation, which includes included or related to SVC method of Python circuitry. Here, if you want to provide the probability estimators, SVM cannot do it, and we have to use something called 5-fold plus K-fold cross validation. K is nothing but number of folds cross validation, which is included in cycle library. See, you can see here, this is a practical problem. How we will be solving this problem? How we are segregating this problem? We will be using something called as kernel function in order to provide non-linear separable line that is like a circular line. If we likewise here, if we draw line something like this, after that we have to draw the hyperplanes parallel to this, like this, in order in such a way that the margin is maximum, and it should or else it should mm, it should get the condition, it should satisfy the condition of minimum 2 by w, norm of w. Okay, thank you guys. The next session will be from starting back. We'll be implementing this particular SVM classification model with the help of Jupyter model. I'll be sharing that. Thanks.